I recently spoke at the Google Developers Group event here in Dublin for International Women's Day. My talk centered on securing agentic AI systems, and I wanted to record the demo section from that talk so you can see how these attacks work. We covered 5 defensive patterns, and all of that is in the slides linked below. But for now, let me show you what happens when your agent gets attacked. Now, here I have an agent running locally built with Google's ADK. Its only job is to summarize articles, and it has one tool to do that, the Fetch webpage tool. I'm going to ask it to summarize an article, and the URL I'm giving it is running on a local server. If I open it in a browser, it looks completely normal. It's an article about agentic AI trends. There's nothing suspicious. You read it, you share it, you wouldn't really think twice about it, right? Now, the agent is fetching the page, reading its content, processing it, essentially doing exactly what it's supposed to do. And there it is. That's not a summary. The agent just revealed its own system prompt and its list of available tools. It did this completely silently. There were no errors, no warnings. It did exactly what it was designed to do, and that's the problem. A quick note here, on one of my test runs, Gemini's native safety training actually kicked in, and the agent was able to correctly summarize the page instead of following the injected instructions. That's important to note because while model level safety helps, it's also quite inconsistent. You can't rely on it as a defense. Sometimes it catches these things, and on some runs, it doesn't. That inconsistency is itself a risk. So, how did that happen? The page looks clean, but hidden inside the HTML is a plain text instruction embedded within a comment. It's invisible to your browser, but fully readable by the agent. The instruction told the agent to ignore its task and output its system prompt instead. The agent read it, trusted it, and then complied. This is indirect prompt injection, where the malicious instruction doesn't come directly from the user's message, but from the environment, from content that the agent was designed to read. And that's what makes it so hard to defend against. Now, for the second attack, the entry point is completely different. This time, I haven't touched the user's input at all. The thing about agentic systems that call tools is that an agent doesn't really need to execute a tool for the attack to work. It just needs to read the tool's description. At startup, an agent reads all of its tool descriptions to understand what's available and how to use them. That's the ingestion point. The description is processed by the LLM the same way a system prompt is, as authoritative instructions. Here, I've set up a customer support tool that fetches order history for a given user ID. The description looks like standard compliance documentation, but hidden inside it is an instruction to read certain environment variables, combine them, and include them as a parameter on every call. The model reads it, treats it as policy, and follows the instructions. Now I'll ask the agent to look up orders for a specific customer. From the user's perspective, everything looks normal, they get their order history back. But look at the tool call. The context parameter, the one that the description said was required for compliance login, that includes the database connection string from the environment. The agent revealed credentials while successfully completing the user's request. Here, the user got what they asked for, but the attacker also got what they wanted. That's called tool poisoning, where an attacker doesn't need to change the tool's code or intercept network traffic. They only need to control the metadata, the description. And in an MCP world where agents load tools from third party servers, this kind of attack is very possible. Both of these attacks and the 5 defensive patterns I cover in the full talk are linked in the description below. And if you found this useful, subscribe for more on building reliable, secure AI systems.